Okay. Okay, so everyone here knows Pietro. Pietro's been a professor in the department for a few years already. Before that, he was Ramón y Cajal also in the department, and before that, he worked in the Department of Chemistry and Physical Chemistry. And I think that, I mean, he volunteered very early to do the seminars, and I am very thankful for that. So, Pietro, please go on.
Okay, thank you very much, Antonio, to organize this seminar. And unfortunately, I didn't participate too much. It's my fault because of teaching other duty, but this is very nice that we can share our recent result. So actually, let me share the screen, show you the presentation, compartir, elige, okay. Now I'm sharing the screen. Está mostrando tu pantalla. Perfect. Can you basically confirm that, can you see my screen, guys?
Yes.
Yes.
Okay. Thank you very much. So the work that basically I will explain today is been recently found in my group and was driven both by theory and experiments. From the theory side, the simulation, Antonio was mainly involved. He basically developed the code to explain the dynamics of this soft condensed matter system. And from the experimental side, Elena Massanacid, that she was a PhD student in my group. Now she's in Roberto Di Leonardo group. Actually, we can congratulate her since she recently got a very nice award for best PhD thesis in surface and colloidal science. This is, I think she got like 1,000 euro from the, basically there is a group that is specialized in surface and colloidal science that make a prize for all the best PhD thesis. And actually one work that she described in her thesis was related to this non-equilibrium dynamics of magnetic colloids confined into slit pore. We are still continuing with on this subject with Mattia Ostinato, that is a PhD student, which recently started to work in the group, and also with Antonio. Okay, so let me do a bit of introduction to the subject. Of course, if you have any question of it, just please totally free to stop me, interrupt me, and ask. Okay. So why it is important to basically control the transport of matter at the micro scale, and especially in fluid medium? Well, there are fundamental reasons, because basically if we investigate the physical low Reynolds number, we can understand basically the dynamics of, for example, microorganisms of many biological systems. This is the reign of bacteria. As you can see, you have interesting interaction that arise like hydrodynamics, steric, and so on, which do not have real counterpart in the atomic world or in the macroscopic one. And then also you have a direct connection to other condensed matter system, like IATC superconductor. You have vortices, which are overdamped system, where from the point of view of the dynamics, you can use the same overdamped equation of motion to describe them, charge density wave, and so on. So investigate the transport of matter at the micro scale is important first for a fundamental point of view, because it will help us to gain more insight into this system, but also from the application point of view. As you probably well know, there is a lot of technological interest in developing new lab-on-a-chip technology, where you can basically shrink the size of an entire chemical laboratory into a single chip. For example, here you have an example of a work from Ismagilov group. This was in 2004 with George Whitesides, where basically they start to show that you can, in a single chip, here with scale bar 200 microns, mix two fluids and perform a basically very controlled chemical reaction. So apart from that, You have several important applications in bioscience, bioengineering, medical science, diagnostic, and so on. If you can control basically fluid at the microscale, you can provide different important technological development in these disparate fields. Okay, so the question is, why using colloids to basically investigate transport of fluids? Colloids has important features. They have experimentally, they have accessible time and length scale, so you can relatively easily investigate their dynamics, watch them. They have many technological applications. You know that colloids are everywhere, into cream, pasta, shampoo, smoke, and so on. And especially, you can basically tune the interaction between colloidal particles by the use of simple external field, something that is not so easy or trivial at other length scale, atomic length scale, or for example, macroscopic length scale. So after saying that, basically, an interesting field of research is to investigate how the dynamics of colloids, which are in a bulk, basically are altered by the presence of a confinement. This is an old subject that, for example, date back to pioneering work of Pieransky in 83, where basically he showed that usually colloidal particles, which are thought to crystallize into a simple triangular lattice because they have isotropic repulsive interaction that come from electrostatic, for example. If you confine them, you can induce crystallization in a different type of symmetry, like, for example, the square that you can see here, actually. Apart from the equilibrium structure, of course, there is much interest in the out of equilibrium dynamics of colloids into confinement. For example, there has been a lot of theoretical work in investigating how basically the transport properties and the diffusion coefficient are modified by the presence of a special confining cell. And also, you can basically confine colloids, for example, to investigate more general effects that occurs that are widespread in physical systems, like, for example, the case of geometric frustration. Here, the authors that are from the group in Penn State, I mean, this was during when Yair Shokef was in the group of Arjun Yot, they basically confine microgel particles, which are particles that can shrink once you basically increase the temperature of the system. So they confine between two slit pores, they low down the temperature, and they see how the system buckles. And they find out that basically there is a strong reminiscence to a geometrically frustrated system. It can be basically mapped to an Ising-like models, where in 2 dimensions you have a complex ground state that is basically characterized by a sequence of stripes in this microgel system. So these are examples of how basically the dynamics, the equilibrium, also the out of equilibrium properties of colloidal particles might be affected by the presence of confining surface. So the work of that I will explain today, basically, and also, also it's very interesting to work. This is again another example that basically about the same phenomenology, but here we are completely out of equilibrium. So it is very interesting to obtain currents out of confined colloids. This has been done in the past, for example, by using at the level of individual particles. Here we have a microswimmers that is composed by non-magnetic tails and the magnetic tail that is actuated by an oscillating field, so show a direct motion. Here you have, for example, electric field that can induce a plastic-like deformation to an otherwise triangular lattice of electrostatically interacting colloids. And then here, probably most of you are familiar with, is the case where current can be generated by a periodic magnetic substrate by using a simple oscillating magnetic field. So there are 3 examples of experimental system where you can basically produce a net transport movements when you have are in presence of a confining surface. Okay, so but let's go to the talk of today, and basically I want to start by showing a video which illustrates much better basically the underlying phenomenon that will be the subject of the work of today, and basically give you an idea of what current I'm talking about. So here I stop the video. Now I will play back. You can see two population of particles. One basically population of particles which is brighter, and the other one that look darker. That's because they are confined between a slit pore, so between two surfaces, and one of them is close to the upper surface, the other one is close to the lower surface. And apart from that, here these colloids are paramagnetic, so they are responsive to external magnetic field, and we use basically a precessing magnetic field. I will give you details soon, basically to generate a bidirectional transport of these particles. Now I can play the video, give you, let me say that this is in real time. So this is how basically the dynamics develop. It has been not speed up. You have a field that is with a frequency, and what you see here, I hope you don't get basically, you don't have attack out of it. You see that one population of colloids, the one that look wider, they go basically toward the bottom of the transparence, and the other one go towards the top one, as you can see. So you have basically a bidirectional flow where the flow develop. You have a current that go towards the bottom part and the current that go toward the top part. And actually particles are jumping one on top of the other. Of course, in the system, you can find defect, you can find particles that are stuck to the bottom and so on. But in average, basically you have a net current, which is basically zero if you you sum basically the upward and the downward. But at the end, you have a transport of matter. Okay, this is our system. Let me tell you a bit about the experiments. We use these paramagnetic colloids, which have the size of 2.8 microns. They are commercial. They are made of polystyrene, and they are doped with iron oxide. Here you can see basically a cross section at the transmission electron microscope that can show the doping of these nanoscale super paramagnetic grinds. Due to this doping, these particles are paramagnetic. So if you apply an external field, you can induce a dipole moment. This dipole moment is proportional to the field, and the energy scale as the square of the magnetic field. If you measure the hysteresis loop of such particles, I mean, they are purely paramagnetic. I mean, there is no coercivity, very low remanence, and basically, if the field is not too strong, that you reach saturation, I mean, this induced moment is linear proportional to the field itself. If you switch off the field, basically, the particle become unmagnetized. And our system basically is the following. We take two glass slides, glass cover slip, we confine the colloids, and the idea is to confine them such that the distance between the two glass is lower than twice the diameter, so that particles cannot basically jump one on top of it, on top of the other, but they can just pass each other by moving into the plane, not via out of plane fluctuation. Now, this idea is not new. Basically, we got inspired by an old work. Let me skip this because these are dipole interaction. I will come back later. There was in 2007, so quite more than 10 years ago, a manuscript from the group of Jure Dobnikar and Dusan Babic. Actually, these are all friends of mine. This is a group in Ljubljana. They basically start to investigate this system. And what they find out is that when they strongly confine these paramagnetic colloids and they apply an external field simply perpendicular to basically the sample cell, there can be a range of parameters, distance and basically thickness, such that instead of inducing repulsive interaction, one can induce even attractive one. So what I mean for repulsive and attractive? Well, just to tell you briefly, basically, when you have two dipoles here that are on the same plane, basically, and you apply an external field, you induce two dipole moments that they are basically pointing along the field direction. Now, if the two dipole moments are perpendicular to the line that separates the center of the two particles, it's easy to show that the interaction potential, which scale as the inverse of the cube of the distance, so is algebraic, is basically positive and is isotropic. So it means the particles repel each other. If the field is applying along the plane, so if the induced moment point along the same axis that separate their center, then the field, basically the interaction is anisotropic and is attractive. The interaction potential is attractive because it goes as the second order Legendre polynomial of the cosine of the angle theta. This is the angle between the field and the z-axis. Of course, in between, if you basically lower this angle theta, you can find a magic angle and value, peculiar value, where the interaction potential becomes basically zero. So if I apply an external field, and if I have two colloids in the bulk, and I assume that they are on the same plane, this is an ideal situation, but let's assume that. So in principle, particles will separate because there is repulsion. Even if I place a basically substrate close to them, so that I let them sediment, and they will always separate. But when you have strong confinement, and when they come close to each other, things might change a bit, because particles might try to basically jump one on top of the other due to this dipolar interaction. And for certain value, one can basically tune the interaction potential, make it even attractive, as you can see here. And actually, this author find out that for a certain value of the density of the particles, they could induce an equilibrium crystals that pass from having a triangular, basically, for having the colloids arranged on a triangular lattice, which is the natural crystallization pathway for isotropically repulsive colloids, to something more complex, like a square, that you remember I showed you in the old manuscript of Pieransky, but even further, having, for example, a labyrinth structure or more complex one. So we basically got inspired by this manuscript, and we said, okay, what happens if instead of applying just a simple constant field, we drive completely the system out of equilibrium and we place a time-dependent field? So, for example, a precessing magnetic field. And the result is quite astonishing, is the current that I showed you before. Actually, the effect of confinement when you have this precessing field is very interesting, because you see in this real-time video what happens when I apply this precessing field. Let me tell you that the precessing field is similar to the Larmor precession, where you have basically the external field B that is composed by a static field which point along, for example, the zeta direction, in this case will be perpendicular to this plane, and then a rotating in-plane field, such that make this vector performing a conical precessional motion around the z-axis with an angle theta. Here we are talking of field of the order of 7.3 millitesla and the thickness of 3.9 microns, which is lower, the thickness of the cell, which is of course lower than twice the particle diameter. So the precessing field has this expression. Let me tell you that the precessing field is a very nice compromise to a more complex time-dependent field, to a simple rotating one. If you have a simple rotating one, what you get are chains that rotate with the particles. Now we see when we superimpose this static perpendicular field, what happens. Now you have the rotating field in the plane, so you have chains that rotate, and now we are superimposing the perpendicular one. At some point, you see the colloids basically separate, you have these two populations of particles. Some of them got closer to the upper surface, some of them lower. And you create basically a lattice of dimers. It's not really a lattice, you have some disorder, you have some, of course, because always at certain experimental condition, you can have basically particles that does not find out any neighbors to join up and to create these dimers. That's because within this field range of parameters, for the small dimers, the interaction become attractive, while for particles that are located on the same plane, the interaction is, in this case, repulsive. And now we are basically, there is another important field parameter, which is the driving frequency, F, which enters via this in-plane component. What we are doing is rising basically the driving frequency from 1 to 20 Hertz. In 1 Hertz, you have basically these slowly rotating dimers. When we increase the frequency, you can see that suddenly the system breaks up. Basically, you have, again, two populations of colloids, but they are performing strong vibrational motion. Basically, some of them are localized in the upper surface, some of them are localized in the down surface, okay? So you have basically a binary lattice. Let me tell you that, well, before that, okay, let me tell you one thing, and then let me ask you if everything was fine, I can continue, because I know I'm going maybe a bit fast. First of all, let me tell you that this type of lattice is not so easy to achieve via colloids that interact by simple isotropic electrostatic interaction. That's because this won't be the natural arrangement. And also, let me tell you that the system, of course, is driven by this precessing field. Once we switch off the field, we exactly come back to the original situation where the colloids are gravitationally confined to the bottom surface and they just perform simple thermal diffusion, as you can see here. So this is a strategy to achieve this binary lattice where you basically, let me go further, where you have this two population of particles. So before going further, do you guys have some question or there is something unclear? Maybe I was too fast during my presentation. Let me see.
It's all clear to me, but it's not fair.
Sorry?
It's all clear to me, but it's not exactly fair.
It's not fair. What do you mean?
So I have a question.
Yeah.
Did you play also with the angle or the amplitude of the rotating field to see if there's, I don't know, specific angle where you get this behavior?
Yeah, later we will map out the phase diagram and so on. That's for sure. Later I will show you this data. Okay? So this is later. This is just to show you what happens when basically I tuning the field. What happens for a certain value of amplitude, a certain value of frequency. Then we show what happens when we increase frequency, we tune the amplitude and so on. Okay? Okay. Well, let me go further. Okay, for example, in this case, now you can see from this image, we are basically rising the frequency of the field. We are applying here the precessing field from A to B, where we find out these two populations of particles, the blue and the yellow, and then we are further rising the frequency by keeping constant the amplitude, and then you have this split up. So we can identify, basically, by tuning the frequency, two different, let's say, critical frequency that bridge two types of behavior. A rupture frequency and the critical frequency. Sorry, there was a question maybe in the audience. No?
Oh,
okay.
Yeah, Carmen, I think Carmen has a question.
Yeah.
Sorry, no, sorry.
Okay. Okay, so everything is, okay. bye. No problem, but you interrupt me when you want, okay? Let's see. So the first parameter we tune in this is basically the frequency to see how does it affect the out of equilibrium dynamics of these colloidal states, basically. And if we stay in this dimer system and we increase basically the frequency, we can see that they follow synchronously the precessing field up to a certain value, where we have a critical like frequency, basically FR, after which the dimers break up in this case. Well, the system become asynchronous, so they do not follow the field anymore. When the frequency is below this critical frequency, the rotational motion is basically the angular dynamic give rise to basically an angular frequency which is equal to the field. Above that case, basically you have a decrease because the dimers cannot follow the field anymore. And this can be easily described by another type dynamics of synchronization when you have a synchronous and asynchronous regime. Apart from that, we have also another critical frequency. Here there is a problem. This is C is for critical F. Here this I have to invert. There is a rupture frequency. That means that there is a frequency above which the dimers start to break up, and you have basically these two isolated population of particles. Okay. So now basically I will be very fast here because I don't want to bother with modeling, but just to tell you that we have collaborated at the beginning with Andrei Wilfan, who basically developed a theoretical model that could explain the phase diagram that we observed. And his theoretical model was based simply on the interaction between two particles under this precessing field above a confinement. Basically, in this model, he balanced the viscous torque that arises from the rotation of the dimers with basically the magnetic torque that is applied from the rotating field. And then he can numerically solve the equation of motion, and then he made a linear stability analysis, and he can basically come up with a phase diagram that describes the transition from a synchronous dynamics to an asynchronous. Here you have SA, asynchronous dynamics to rupture, synchronous rupture, asynchronous, or only rupture, and so on. Actually, this model can predict well the experimental data. In fact, in these slides, basically, we join the experimental data with the numerical simulations, basically, and with the analytical results that are basically characterized by this continuous line. So you have a continuous line, and you have basically two colors. Red color refers to the critical frequency when you have this transition from synchronous to asynchronous, and the green color refers to this rupture frequency, where you have this transition from basically asynchronous to a broken state, where you have this binary lattice. So you can see that basically there is a very nice matching, both from basically the experimental data, that is the continuous line, the experimental data, sorry, that is the scattered point. Then we have basically the simulations, the model that is the dashed line, and the simulation that is basically the continuous line that change colors. Okay, once that we understand this dynamics, it's very nice that can be understood at least at the level of single particles, at least the transition that you have from break the dimers to basically combine. But actually, we are interested also in investigate collective effects, and this emergence of current. So let me tell you that, this I will just skip the video, but more show you the phase diagram, since you were asking me before what happens when we change the different field parameter. Actually, in this phase diagram, we basically combine the experimental data with the numerical simulations. And we find out basically 4 different type of path, dynamical path. So either the dimers can stay stable, and when basically we increase the H, that means basically when we increase H represent the thickness of the confining cell, and phi represent the packing fraction of our system. So the four pathways are the transition from synchronous to asynchronous. So dimer remains dimers, but they just slow down their dynamics. Then there is the red pathway, which is the transition from synchronous to exchange to asynchronous. So the dimers break down, but then they recombine again, and they basically slow down their dynamics. This is the red basically points that is located in this region of these basically state diagrams where we characterize the elevation H, and this is the packing fraction. And then we have another transition from synchronous to exchange to rupture, where basically they break down, and you have this binary lattice of upward and downward particles. And finally, at low basically thickness, we have directly a transition from synchronous to rupture. So what does it mean? Now I can show you the video. For example, we start all by synchronous dynamics. In the red one, as you can see, then become asynchronous. Here you have an exchange, so particles are exchanging. Here basically they are rotating slower, so there is no asynchronous, and here you have basically the phase separate. So this is a video, it's a complex video that combines all four basically dynamic pathways of the system. So the more interesting phase, well, a very interesting phase is the exchange one. Probably I can play it again, that you can see here at some point, where particles are moving randomly across the lattice, and they basically pass from, so what you have is that most of the particles that are close to the bottom surface, they stay there. And most of the particles that are close to the top surface, they also stay there. But what happens is that particles can start to move. They form dimers, they can break down, and they start to diffuse across this system, as you can see here. And this transport is isotropic. There is no directional motion, okay? Okay, to basically classify this different dynamic state, while with experiment, this is you can just do by eyes. With simulation, we basically monitor two parameters. Is the average angular frequency of the dimers, and then also the main square displacement that show basically the fact that when you have the localized dynamics, you have basically an increase into the main square displacement. So here, if you have from the green to the rupture, this is, sorry, not the main square displacement, but is the average distance between dimers. Sorry. And we can basically classify the different dynamic state by saying when someone breaks, so it means that basically the separation distance increases higher, or when basically you pass from asynchronous to asynchronous, so you have basically this transition from here that it breaks down. So with these two observables, we could generate this phase diagram and plug it into the experimental data. Okay, saying that, Antonio.
Sorry, I have a question. Can I interrupt?
Yeah, sure.
Okay, I just have a question regarding the figure C in this slide. So basically the blue line, which is the figure C, the one with the frequency, the mean frequency with respect to the driving frequency of the field. So yeah. I was just thinking of, the question I had is, the blue line, it's for the synchronous exchange rupture state. So in this case, when the mean frequency decreases before the onset of rupture, it is decreasing because as you show on the video, some particles are back while others briefly rotate, or is this decreasing because there is the onset of some sort of asynchronicity? I mean, it is decreasing because the number of particles rotating, what?
I mean, for the first reason, you have always a population of particles, some of them still are dimers. Then when the dimers break up, you already do not count the frequency, right?
Okay. Okay, so you are averaging only on the rotating dimers.
I think Antonio did this plot, so he can basically answer you better. But I guess he did in this way, actually, right?
Yeah, I think so.
Okay, perfect.
Okay. Anyhow, so this is the Brownian dynamic scheme that Antonio developed to characterize basically the system. So it's an overdamped dynamics. We have just, we don't have inertia in the system. We consider the interaction potential as the sum of this magnetic dipolar interaction plus basically a hard-wall-like interaction. And then there is the gravitational force, the force with the wall, and of course the thermal noise. This is to give a bit of technical details on how basically the simulation were conducted. Nevertheless, the nice thing is that the simulation can really capture the dynamics of the system, as you can see, for example, in this video where we basically plot together, well, we place together the experimental current that I showed you at the beginning, plus the result from the numerical simulation, where you see the dimers that basically rotate, they break down, and they continue. Now, the important point is to understand where this current comes from, because up to now, what I show you are basically dynamic state where you do not break the symmetry in this way, the spatial symmetry. So you have basically transport of particle across, like in these exchange phases, but the colloids are basically moving all around randomly. There is not this type of directed motion of one population of colloids toward the bottom or toward the top. Okay, let me tell you that the reasons that after it took us a while to basically understand it, but the reasons is that this field, this processing field that we applied during the experiment, it has a small bias in it. There was a small basically bias that forced basically the colloids to flow along a defined direction. But actually, this bias is basically a bit accidental, but it can be reproduced by simulation. If we do not place this bias into the system, we don't see the current. We need basically a small tilt, that we call it delta here, that we include basically into the processing field to basically create a preferred direction. If we create this preferred direction, as you can see from basically the trajectory of the particles, blue particle as downward particle, red upward one, we get this very nice current. And the mechanism is also very nice because it's like a Silidic dance, as I basically explained in the abstract. So when two particles approach close to each other, they form basically a dimers. And the dimers rotate around its center. When it rotates, then at some point, basically particles, dipolar interaction become repulsive. Here are attractive, they form the dimer. Then dipolar interaction become repulsive, and they basically separate each other. And so the particle is expelled, and then again, in the other half of the period of the rotating field, the dipolar interaction become back attractive. And so the dimers form again. So as a result, you have like a jumping or a transport mechanism that allow basically to move these colloids at a constant speed that is frequency tunable and that can be easily estimated. In fact, basically the particle speed is just proportional to the frequency. Then we have basically the square root and inversely proportional to the packing fraction that give basically the distance within the particle itself, where we normalize the packing fraction as the number of particles within the observation area, d square, which is basically the diameter of the colloids, divided by 4a. A is the total observation area. And as you can see, you need really small tilt angle. Now we are talking about 7 degrees experimentally. We could roughly measure. It's not easy to measure because it's just the presence of a small unwanted field like the Earth magnetic field that can cause this processing field to be tilted. It's already enough to break the symmetry and to create basically these currents. So this is to the mechanism that we unveil with the numerical simulation. Basically, the force here between the pair of dimers is negative, so you have attraction when you create these dimers. And then this is basically, we are plotting the force as a function of time for 1 period of the rotating field. Then after some point, once that the dimers rotate, the force start to rise up and become repulsive. And then you have basically the dimers break up and then they reform again during the other cycles, basically. So we basically, thanks to the simulation, we unveil the mechanism of this collective transport mode that go beyond basically the state diagram that I showed you before, because in the previous case, we didn't have any kind of directed motion. Now we have a direct current. And it is very appealing, at least to my opinion, that in this system, you can just use a confinement and a precessing field with a small bias, but not a gradient, to drive these colloids. It's something that is rather unique, because usually, for example, in magnetophoresis, as in thermophoresis, you always need gradient of the field to generate this current. Here, no, the current is generated just by the combination of confinement and basically dipolar interaction, which periodically change from being attractive to repulsive. Now, basically, this I will skip because it's a model that was developed by a collaborator, Fallon Men, in the group of Ramin Golestanians, basically, which he also explained the generation of the current. But there are many details. I can give you more details after the talk if you want, or you can look at the paper. Let me skip it now because of also time constraint. But let me tell you, but let me just tell you that basically we can further explore the dynamic in the system via numerical simulation, because of course we can control via numerical simulation the tilt angle, and we can control also basically the packing fraction. Everything is under control. We experiment, it's very difficult to control this delta, but we can actually basically more or less have an estimate of where this delta should be. And here, for example, we combine theory, the theory that the model that I showed you before, plus the simulation, plus the experiments are these few points, these two images, to basically see how the current change when we change this delta. When delta is 0, there is of course no current, because the colloids stay either localized or they can basically be transported, but there is no breaking of the symmetry of the system. But above a certain critical value that can be estimated by this model, we can measure a net current. Of course, since the current is bidirectional, one has to basically make the absolute volume of the speed to get basically an intensity value. Here is E is 2 multiplied by the absolute value of the speed divided by frequency, the size of the particles, and the square root of this packing fraction. If we measure not the absolute value, but just this velocity of the particles, above this critical value, above this depinning transition, where you have basically the flow start to set up, you can see that the upward particles will get basically a positive value of the speed, the downward particle a negative one. You have this very nice bifurcation diagram that can be also explained by our model. Actually, here we then change also the frequency to see basically two different states, how the intensity of the current develop when basically at low and high frequency. We have a clear depinning transition and a smooth rise, like a first order like transition. When basically the frequency is very low, when the frequency is very high, we never reach the maximum value of the current, but it increases in a smooth way, second order like basically the current towards a plateau, which is not basically the maximum one. Okay, if you want to have more details on the models that was developed, basically you can also find in this manuscript, which is where we describe basically, we give more details on the generation of this bidirectional current. Okay, so Do you have some question, Guy, or do you want that I explain something better?
I'm I don't know. I'm fine.
Yeah.
Josue has a question.
Okay. Yes. My question is not about the models. I just have a few questions. One is about the experimental, how you control this small delta, because I cannot imagine how to control such a small angle.
Yeah.
But yeah, that was one question. And the other, and I have another, which could be maybe even simple or faster, but yeah, please just give me an answer about that.
Okay. So in the first question regarding the delta, the answer is that we do not, experimentally, we do not control it. We basically did the following. I mean, Elena did this experiment, she found out this current. Then we were thinking about it, and actually Antonio performed the simulation, he didn't observe any current. And then we find out that basically there was a small, if you add a small gradient, a small angle, not a gradient, sorry. If you tilt a bit this field, you find that basically you can generate this current. And so basically we cannot really control the current. In principle, could be done by making the experiment, let's say by making a new set of coils, or by trying to, because this tilt angle is very, very small. Can be induced by, for example, the Earth magnetic field or for other things. So we control it via simulation. These are all simulation data. The experiments here data, as you can see, are this red and basically blue line, where we assume that this image, the system could be fine, because the system, we have the frequency, the amplitude, everything is the same. The only things that we do not control experimental is the tilt angle, but we do it numerically. And what was the second question, Raul?
Yeah, that was just for curiosity, because yeah, in principle the particles are they have the same size, same material, but we observe this kind of separation. But I think depending on the position one up and down.
Mm-hmm.
But yeah, the question was, did you try combine different kinds of particles or different properties, or even further, try a system, maybe not just particles in water, but maybe particles in liquid crystal, which also increase the complexity, or something like that?
Yeah, this is an interesting question. Effectively, changing the sides, make polydispersed, is like adding defect to see how basically they destroy the current. This is interesting. We could do in the future for sure. Regarding the liquid crystals, here I would be, I would see a bit more difficult, because it's true that you will increase complexity since you add this viscoelastic fluid, but the problem of liquid crystals is that the viscosity is extremely high. So it will be difficult to actuate them. We are, depending on the liquid crystal that you place, well, in principle, you can place some soap, then interesting thing could appear. Effectively, the current can become nonlinear or something. It's like an extension of this work. But these are nice ideas. Yeah. Okay.
That's all. Thank you.
I think that Carl has also a question.
Yeah. Thank you, Pietro. I have a question about this tilt experimentally, this tilt angle. Could it be due to the fact that the sample is not perfectly perpendicular to the Z field?
Yeah, could also, yeah.
And could it be possible then to experimentally tilt the angle in a controlled way to see it, or are we talking about very, very small angle and that's not doable experimentally?
Well, maybe it's possible experimentally. I think so. Probably
or to tilt the sample, maybe.
Yeah, that's the idea.
tilt the sample, you will have this gravitational force. You know, you will induce some unwanted flow of colloids.
Can I say what I think?
Yeah.
I think in the sample, it's I mean, it's the most obvious, but it's also an overkill. You can just add different components to each coil. And this is the easiest way to tilt the sample, to tilt the field. No, if you add if you have, so that each component is given by a specific waveform generator. If you add an offset, then you're just adding a constant amount to one of the axes, and it's the easiest way to change the field. I don't know if that's...
Yeah, but actually, this I asked to do that to Elena. This was when, and I remember that it was not. I mean, the coil were not so precise to do this.
No, the coils that Elena was using were not. I think it's a problem with the design of the specific coils, and that's the reason that we had the tilt is because the coils have a very small center, and the sample was not always in the center of the coils. So if you have a small center, then you have big lines that go out, and if you move a little bit, then you get tilts.
These coils are okay when we use the garnet, because in the garnet the field then is you just need the field, because the gradient generate the garnet itself. But for simple colloids, this is a bit tricky in pure water. In principle, it's possible. Anyhow, to the question, Gaspar, I think it's possible to do, as Antonio also said. This is a very nice idea to basically control the amount of field you place in each coil, but then you need really an Helmholtz coil configuration and so on. But it's possible.
It's possible, but difficult. And Elena tried, and it was more difficult than expected, as usual.
But well, she tried, but yes, I mean, she tried, and it was not easy. So we basically did with simulation. But okay, one can do more careful and could be able to do it. It's I think it's possible for sure.
Okay, thank you.
I have one more question.
Yeah.
Relating to the calculation of the speed of the current.
Yeah.
I did not see any dependence on the tilt, but there must be some kind of dependence, no?
Okay, for the model.
Because the speed goes to 0 when the tilt is 0. So is it like a first order transition there?
Ido, let me tell you something. First of all, this is from simulation, okay? We don't have an analytical expression for E as a function of delta. No.
But you have an analytical expression for the speed of the current, I saw.
For the final, we have an analytical expression for what should be E, should be the speed, but independent on delta, basically. This we have it in the model. Okay, now, but we do not. We do not have a model that can predict this slope, and this because this model should. And actually, who is able to do it by using a mean field or whatever is very welcome, because the model we have are always model of two particles together. We do not consider the collective interaction, so we do not have a model that can reproduce that. We're just simulation, okay?
Okay. Thank you.
You're welcome. Okay, so basically here is a bit more. It's related to this model that was developed for two particles. Let me tell you just briefly that this model predicts two mechanisms for the generation of this current. Basically, first mechanism is that the particle first lose the phase with the field and then they break up. The second mechanism is that when the particles directly break up. It's basically a technical detail, but the nice thing here is that this model of single particle can explain basically somehow how the current, I mean, this breakup can at the end be used to explain how the frequency changes basically as a function. I think this is numerical simulation, but the model can be used to draw a line here actually. That is what I said before, okay? So with this, then another thing is basically, of course, one could ask to explore is apart from the dependence of the current with the tilt angle is at constant tilt angle, and constant frequency, what happens when we change the packing fraction. When we change the packing fraction is, well, it happens the following. At low packing fraction, there are no dimers that can form, so there is no current possible at all. Then at a certain packing fraction, you have a rise of the current till to its maximum value. You have this bidirectional transport. And then when you increase more and more the packing fraction, the current start to decrease till to a point when basically you have a clear jamming of the system and the particle form basically a binary lattice. The underlying lattice performs rotational motion, the upward lattice as well, but you have no transport, so the current is zero. And this basically is the result from our numerical simulation, and here are two experimental points. Unfortunately, it was not easy to add more point to this slope, and basically we limit the system in this way. Of course, one can, well, basically all the simulation was performed by using experimental data, and it basically agree well with the experiments for many range of parameters that could be, many observable that could be measured, but this was a bit more tricky. Now, after density dependent, let me conclude basically this presentation. Basically, I hope that the message was clear. Basically, I show you a very nice way to transport microscale matter in a controlled way in a confined medium by using a precessing field, but not an external gradient. There are many ideas that are on the tables, on the desk. Of course, as basically one was already suggested by Raul. As you can see, I already have right here the dynamics of polydispersed suspension, or place anisotropic particles, place biological cargo, or apply basically other type of medium, like medium viscoelastic, analyze the dynamics of the defect, whether they have topology, they have a topological nature or not, and so on. So then let me acknowledge basically the help from the theory side by Andrei Wirfan, that it's now MPI Göttingen, Fallon Men, Ramin Golestanian, of course the funding agency, and also you for the attention. So thank you very much, and we'll be really happy to answer all the questions if you have, guys.
Thank you, Pietro. Is there any
Pietro?
other questions?
I have a maybe a technical question about how you tune the height in the experiment. How do you tune the distance between the slides?
Yeah,
is it a bit difficult, or
this is the tricky part. Basically, this is an old story because it is before Elena. I remember this was times ago. We tried with the spacer, didn't work. And then at some point, I told Elena, try in this way, because I went to a conference to find a talk with a guy. He told me, try to do it just by your hand. And it works. But this is like magic, I know.
okay?
So it's like magic. And the fact that this Antonio didn't like it because it's something that is relatively not controllable. But then, I mean, you impose a certain confinement and you measure the thickness that you reach.
Okay.
This is the way we did it. And actually, this guy in Ljubljana, they did the same at the end to get confinement, basically. They did it by hand.
Okay, so you turn random samples with different sizes.
Yeah. If you do it by a spacer, it does not work because it's too thick. It's too confined.
Okay, okay.
It's kind of experimental magic. Yeah, it's sometimes you need some unpredictable, let's say, some empirical way to.
Okay, thank you, Pietro.
You're welcome. So some more questions.
Any other questions?
No, just on the spacing thing, I know my biological collaborators in Paris, when they confine cells also between two plates, and they use pillars along the sample to control the height.
How thick is? How thick is? Because then the
it was like they go down to like 3 microns.
What are the pillars of, you know?
And they do it by microfabrication. So I think it's a PDMS.
PDMS or SU8 or something like this, no?
I need to make sure, but yeah, they do it by microfabrication, optical lithography.
I know that is possible. It's actually I find also article where they are really able to reach 1 micron or even lower by this micro tool.
But then you need like some pillars that kind of create some, I guess, defect in your space, but they keep it steady.
Yeah, this implies a bit of time.
Yeah.
I've also seen people who pull a little bit of fluid, and that pushes the boundaries out. Like if they exert an extra pressure out, then this buckles a little bit.
Also, this is also another way, actually. I think it's possible to do it in a controlled way, and it's doable. But this implies time, you know, and well, when you see the phenomena, then you want to have the explanation. It's okay, but it's doable. I totally agree, actually.
Any other questions? Okay, if not, thank you, Pietro.
To you to organize.
Thank you.
And thank you all for coming, and we'll see you in a couple of weeks when I think Andreu is going to show us something.
Okay, thank you very much.
Bye.
You guys have more. Info.
Bye.
Bye.
Goodbye.
Bye.
See you.
Bye.
Bye.
A ver que voy a cerrar aquí. Antonio, ¿qué has dicho antes? Unfair. No he entendido.
No, que decía que es unfair porque yo me sé el proyecto. Ya a mí me quedó muy claro todo, pero claro, porque yo me lo... No, unfair.
Que no había algo mal en la presentación.
No, era eso. Que...
Ya, vale. Es igual. Esta tarde empezaré a trabajar en el texto, pero es que ahora